Hello everyone, welcome to the course Introduction to Lambda Calculus. I am Rajdeep Niyogi from the Department of Computer Science and Engineering, IIT Roorkee. Today we will understand why Lambda Calculus is such a beautiful and powerful foundation for computation and for modern functional programming languages. We will give the motivation and compare Church's model with Turing's model and then learn the basic notations and see Turing and partial application in action. Before we commence our discussion on Lambda Calculus, let us see the origin or the etymology of the word calculus. It comes from Latin calculus, meaning a small pebble, the kind used for counting an early abacus and tally boards. From that practice, calculator meant to reckon or to compute, which is where we get calculate. Over time, calculus broadened to mean any systematic method of computation. When we say lambda calculus, we are using that older, broader sense, a formal system for computation. Here using functions and substitution rather than numbers and limits. In short, from pebbles for counting to a full-blown framework for reasoning about computation. Lambda calculus captures the idea of computation purely as functions, no machines, no memory cells, just function abstraction and application. This minimalism is what makes it so elegant and so general. Today's agenda, we are going to first discuss the core motivations behind the development of the lambda calculus. Then we are going to discuss the two models of computation, one developed by Church and another developed by Turing. The next one, we are going to give notation of lambda calculus, and then we are going to see partial application of functions that includes Turing. Lambda calculus was developed by Church in the 1930s. Alonzo Church was an American computer scientist, mathematician, logician and philosopher who made major contributions to mathematical logic and the foundations of theoretical computer science. He is best known for the lambda calculus, the Church-Turing thesis, proving the solvability of the Entscheidungs problem, decision problem, the Church-Rosser theorem. Alongside his doctoral student Alan Turing, Church is considered one of the founders of computer science. Let us begin with the core motivations behind lambda calculus. So the first motivation comes from the formalizing the notion of computability. Mathematicians wanted a precise definition of what it means for a function to be effectively computable. Church introduced lambda calculus in the 1930s as a formal system to capture the idea of computation via function abstraction and application. The goal was to answer questions like, what does it mean to compute something in principle, regardless of any specific machine? So the idea here is computation means functions and applications, and the core operations in this calculus are abstraction and application. Now let us see briefly what we mean by effective computability. Effective procedure is one that satisfies the following conditions. Each instruction is unambiguous and it has finite length. Each instruction can be mechanically implemented. After a finite number of steps, either a result or a yes/no answer is produced. When we are talking about a decision problem, we say yes or no answer is produced. When you are looking at a computation like addition of two numbers, we say a result is produced. Now let us look at these 3 points very carefully. So suppose when we say we are trying to compute a function, so the function computation means it involves some way of achieving the result or the answer yes, no. So as if suppose we are giving it to an computing agent who might be a human, so some instructions. Now the instructions should be unambiguous in the sense that there cannot be multiple meanings of the same instruction. It has finite length, meaning that it cannot be so long that looking at it and going through it and then interpreting the meaning becomes very difficult. So it has to be a finite length. Each instruction can be mechanically implemented. This means that we can carry out the implementation, that means executing the instruction. We did not apply any mind or we need not apply any thought. It can be just done by looking at it. No other thought process or mind would be involved in computing this instruction. Next, this set of instructions or the sequence of instruction that is provided to us, we will carry out in a finite number of steps. After that, we are going to come up with the answer yes, no or a result. So let us illustrate this idea for different functions. So first let us consider effectively computable functions. The examples are addition of two numbers. We know from our school days that there is a simple method of adding two numbers. Now, GCD of two numbers is a very interesting problem. It was the algorithm for GCD was given in Euclid's algorithm. It is also called Euclid's algorithm. It is more than 2000 years old. So, the idea about the GCD of two numbers, so we will illustrate with an example. So, suppose we have to compute the GCD of two numbers 5 and 15. So, the instruction says that the larger number will be replaced by the difference of the two numbers. So, we replace 15 by 10. Again, the larger number will be replaced by the difference of the two numbers. So, 10 will be replaced by 5. Then there is an instruction that if the two numbers are same, then you stop and return any one of the numbers. So, the answer here is 5. So, what we have in this example, we have two instructions. One is replace a larger number with the difference of the two numbers, and another is if the two numbers are same, then we stop and we return one of the numbers as a result. So, this is the idea of a effectively computable function. Now, we look at a function that is not effectively computable. So, that is called the halting. One such example is a halting problem. So, halting problem is like this. So, halting problem we have, so suppose there is a program P written in your favorite language that takes input x, and we want to design one function or a procedure that we name as miracle. Miracle will return either yes or no. It will return yes when P stops or halts on input x, and if P does not stop on input x, it will return no. So, this is what is the function miracle. Now, suppose we have designed such a function miracle, then this will lead to logical, we can design another function that will lead us to logical inconsistency, that is contradictions. Thus, it can be shown that such a program, that is such a function miracle, does not exist. So, had this program been a reality, then we could have our compiler to say that when the program P does not stop on input x, the compiler will say, look, it is a non-terminative program. That is not the case. So, hence miracle does not exist, and this is an example of a not effectively computable function. So, continuing with the core motivations behind lambda calculus, the next was the decision problem or the Hilbert's Entscheidungs problem. So, this problem was first proposed in 1928 by David Hilbert and Wilhelm Ackermann. So, they asked the question whether there exists a mechanical procedure to decide the truth of any mathematical statement in first order logic. Now, first order logic is an extension of propositional logic that includes two quantifiers, existential quantifier and the universal quantifier. So, that means if you are given a statement in that logic, we take it as input and we will tell whether it is true or false. So, Church showed using lambda calculus that there is no such general algorithm for this problem, and that result is known as Church's theorem. This was a profound early result in computability theory and a precursor to undecidability proofs. Almost at the same time in 1936, Turing also showed that there is no such general algorithm, but his idea was via another tool that is called Turing machine. Via Turing machines, Turing showed that there is no such general algorithm for solving this problem. Later it was showed that the Turing machine developed by Turing and the lambda calculus developed by Church are both equivalent. That means one can simulate the other. Moving ahead, the next motivation is to give a minimal foundation for mathematics. At the time, formal logic and set theory like Russell's and Whitehead's Principia Mathematica were seen as foundation of mathematics. Church sought a minimal function-based foundation instead, eschewing sets and logic in favor of function abstraction. The idea was to represent everything using functions. Lambda calculus was simple yet powerful enough to serve as an alternative foundation. The next motivation is to study of functions and functional abstraction. Church wanted to explore how a complex mathematical objects could be defined purely in terms of functions. Lambda calculus allowed the definition of arithmetic, data structures and logical operations using nothing but functions. Now, we look up the two models of computation, Church model and Turing model. Now, computation in lambda calculus is done using function abstraction and application, whereas in Turing machine it is done using symbol manipulation on an infinite tape. Now let us see how a Turing machine works. So the Turing machine consists of an infinite tape that stretches on one side, the right hand side, and it cannot go beyond this point. So we have a delimiter. So this marker says that the head cannot move to the left of this point. So there is a head. The head cannot move to the left of this point. So one end is fixed. The head can move right 1 unit, and also the head cannot erase this marker. It can erase these symbols 1 or 0, but it cannot erase this left hand marker. Now there is a finite control. That means there is a finite number of states. So suppose the state is S0 and the head is say here. So we define a configuration of the machine as these two things, the head, position of the head and the S0. So if S0 is my current state, let us say S1, S0, S1, so on. We have S0, S1 and like that. And we have another special set of states called halting states. So S1 is my current state and the head is at 1. Then there is a rule that says, okay, you stay in S1 but you move 1 unit to the right. That means the head now moves to this point. This is one thing that is allowed. Similarly, the head also can move 1 unit to the left. So we write left. Now, doing this way, we say that when the machine comes to a configuration that contains the halting state, then the machine stops. And thereafter, the transition function that we have shown, that is undefined. And these are called the transition function. That means you are moving from one configuration to the other. It is undefined when the state is a halting state. So these configurations contain the state. So the operation is defined on, so it relies on what is called a state based. Unlike this sort of state based approach, lambda terms evaluation or computation in lambda calculus is quite different. So here we start with a term and we apply a rule and obtain another term. So that is called term rewriting. So here, for example, we will take illustrate with an expression, arithmetic expression, say 2 plus 3 multiplied by 5. Now in the rules of arithmetic says we have to apply multiplication first. So we will obtain 2 plus 15 and thereafter we will get 17. So this is our term T1. From that we applied rule T2 and there we applied T3. Now at T3 no rule can be applied because it is the simplest form and we cannot proceed any further. So unlike we have a set of states, we do not have a set of terms. We start from a term, apply a rule. That means we are simplifying the term, go on doing until we cannot simplify it any further. So this is the idea of lambda calculus, computation in lambda calculus. So lambda calculus, the functions are called lambda definable functions, and Turing machine, they are called Turing computable functions. So examples are, we will later also discuss all of these in detail. So they are like Church numerals, the Y combinator, the beta reduction. Beta reduction is a method of transforming one term to another. And in Turing machine, we have notions like states, tape, transition functions, head movements. Evaluation in lambda calculus is reduction of expression, so term rewriting. In Turing machine, it is a transition of machine states through tape symbols. So the strengths would be that in lambda calculus, it is a simplicity and abstraction. It forms the basis for functional programming. Turing machine on the other hand, it is intuitive and mechanical, forms the basis for imperative programming and real computers. The applicability of lambda calculus is in logic, type theory, proof assistants, functional programming languages like Haskell. Turing machine applications within complexity theory, automata theory and computer architecture. Now the limitations of these two models, lambda calculus is harder to visualize as step-by-step procedures. So the abstraction, although it looks very elegant, how the computation proceeds, it is very hard to visualize. We are going to illustrate it in the next few lectures. And Turing machine on the other hand, it is less elegant for representing high level functions, although the elementary steps look very intuitively clear. Now we come to the Church-Turing thesis. Anything that can be effectively computed in principle can be computed by a Turing machine or expressed in lambda calculus. It has been proven that every lambda definable function is Turing computable, and every Turing computable function can be expressed in lambda calculus. This means the two models are computationally equivalent, although they are philosophically and technically distinct. The philosophical differences are abstract definition of computation in Church model, whereas it is concrete machine-based simulation in case of Turing model. In Church model, it is aligned with mathematical logic and proof theory, whereas the Turing model is aligned with mechanistic views of computation. The Church model is more foundational in functional programming, whereas the Turing model is more foundational in practical computing systems. Now, we will illustrate the equivalence of the two models using this function add. So, this will give us the idea of how the Turing machine really works with a concrete example. So, as before, we take the head, and our input is two numbers 3 and 2, but it is encoded in unary. That means 3 is represented as 3 ones. So, we represent it as 3 ones, and then we have a delimiter. We say plus, we will separate these two numbers. So, we have 1 and 1, and then we have the blank symbol. So, this is the input, and our goal is to obtain 5, that is, there will be a sequence of 5 ones. So, the instructions are given as first instruction says that scan right to find the plus. So, the head was initially here. So, it moves one unit to the right, then it moves another unit to the right, then it comes here, then it comes here, and it finds the plus here. Then the instruction number 2 says replace plus with 1. So, that means now we are going to erase this and we are going to write it 1. Extra 1 we have now obtained. Third instruction says move to the rightmost one and replace it with a blank symbol. So, again the head moves here, the rightmost, but how am I going to find the rightmost symbol? So, I move to the point where I reach a blank symbol. Now, I know it is the end of that word. So, I come back one unit. Now, this ensures that this is the rightmost one. Now, this rightmost one, it says you replace it with a blank or is hyphen, whatever it be. So, now what we have obtained, the final tape contains 5 ones, which is representing number 5. So, this is how the Turing machine works. So, all the steps are intuitive, and we know how the execution also done in our mind. Also, we can do it quite easily. Now, we see that we represent this in lambda calculus. We will do this first in this way. Suppose x and y are two numbers and addition is allowed, this operator plus is allowed. Then we say, we write this as lambda x dot lambda y dot x plus y. This says if it is supplied with the two numbers 2 and 5, it will obtain, it will 3 and 2, it will give us 5. But suppose this plus is not allowed, plus symbol is not allowed. Later we will see in pure lambda calculus there is no such symbol like plus. So, we have to obtain plus in some other way. So, then with our expression will be as given here. This function is quite complicated. If you are seeing it for the first time, it is very involved. So, the idea here is now the inputs are not like here we can supply here 3 and we can supply here 2. So, here 2, 3, all these things are represented as Church numeral. That means everything is a function. So, 0 will be represented as a function, 1 will be represented as a function, everything can be represented. So, m here mn are the inputs and they are represented, 3 is represented, 3, 2, they are represented as Church numeral. And then this, so the idea here is we are going to extract from the body of this term n number of f's and m number of f's. So, total we are going to get m plus m number of f's, and that represents the number 5. So, this is the idea about the computation in lambda calculus. So, the representation though is elegant, as we said, the working of it cannot be done in the mind so easily. Whereas, for complicated functions, this program that we have written, a Turing program, we can say that would be very involved, but the elementary instructions are quite intuitive and you can do it in the mind. So, that is the difference between these two concepts. So, why lambda calculus? It is highly relevant to functional programming because it forms its theoretical foundation. Some salient features are, these things are also part of Haskell. So, it consumes one argument at a time, that is called currying, and higher order functions means a function whose argument or result is a function, and then function composition. We can compose two functions. So, now we come to lambda notation. So, a conventional way of writing a function is we write fx is equal to x plus 1. So, here f is the name of a function, x is the argument, and the right hand side of equality is the body of the function. So, we sometimes also say x as the input parameter. So, now we see that the name of the function is irrelevant. So, that means we can replace f with g. So, it was gx is equal to x plus 1 will mean the same thing. Now, the argument name is also irrelevant. We can replace x with y. So, it will be same, fy is equal to y plus 1 will mean the same thing. So, let us go a step further by not even writing the name of the function. So now what we obtain is, we do not write the name of the function as fg, so we write lambda instead. So lambda x is used to denote that it is a function, where x is the argument and the body of the function comes after the dot. So this represents our function fx is equal to x plus 1, and this is in the anonymous mode, and this is called function abstraction. So the body of the function is written after the dot. This is the body of the function. Now if I have multiple arguments, so I will have lambda argument 1, argument 2, so on, then after the dot, this one the body will come. So for example, we have seen the add function. So this is the body of the function, and there are 4 inputs. So we write lambda m, lambda n, lambda f, lambda x. So now f of 2 will be expressed in this notation as lambda x dot x plus 1 and 2. So this parenthesis is important. So this part is the abstraction, that is the rule, and then the 2 is the actual parameter that we are passing to this function. So x will be called also as a formal parameter, and 2 is called the actual parameter. We know from our programming knowledge that we call this, that means we are calling a function with actual value 2. So when we do this, what happens here, how it works is, x will be replaced with 2 and we get rid of this lambda x. So what we obtain is 2 plus 1 is 3. So this process is called beta reduction. So here f2, the earlier we used to write f of f bracket 2 is written as f2, just as in sin theta. In sin theta we write the function, then the argument. So you see that why this separator parenthesis is needed. It is because if we had not written, then we would have read it like this, x plus 1 and then 2. So that means this space has no meaning. So this means it will be lambda x dot x plus 12, which was not the intended thing. We started with x plus 1, so now it becomes, so that means we should have this separator. So this is the all the abstraction, and this is the application. So this is called function application. So now we have what we have achieved out of it, we have obtained a clear distinction between function and its value. The conventional notation does not distinguish functions from values. This is another nice thing about the notation of lambda calculus. Now we in lambda calculus we work with consume one argument at a time. So this technique is called carrying. It is named after Haskell-Brooks carry, that transforms a function of n arguments into a sequence of n functions that each take a single argument. It uses the concept of partial application of a function, that is, it applies one argument at a time. This idea is due to Moses Schoenfinkel, but it was named after Haskell Curry, who introduced it independently. Haskell-Brooks Curry was an American mathematician, logician and computer scientist. He is best known for his work in combinatory logic and the Curry-Howard correspondence. The 3 programming languages Haskell, Brooks and Curry, and the concept of currying, a method for transfer functions used in mathematics and computer science, are all named after him. Now let us see an example of currying. So this one says, first line, fxy is x plus y. It is a function of 2 arguments x plus y. When we say currying, we are writing it is lambda x dot lambda y dot x plus y. For the sake of understanding, we have introduced the parenthesis, although it is unnecessary. So it has to be read as f curry lambda x dot something. Now lambda x dot something is the body of lambda x. Now what this something has? It is again a function of one argument, that is y. So this is the body something. So it is again a function of one argument. So what we have done is that we are having all the time a function of one argument along with something. So in lambda calculus and also in Haskell, all functions are carried by default. It is a 2 argument function written as a chain of single argument functions. So we supply arguments one at a time. So we have colored it. So here lambda x lambda y dot x plus y, the arguments values are supplied. So x is mapped with this green and y will map. So first we are going to supply x with 1. So we are transforming it to lambda y dot y 1 plus 1 2, and then 2 will be supplied. So we are going to get 3. So x becomes 1 and y becomes 2. So we are always working with one argument at a time, and thereby we are coming up with the final result. Now why is carrying useful? For partial application, it allows applying to a function to some of these arguments and deferring the rest. That means we could have only applied x, the value of x, and kept it like that. It is okay in lambda calculus. So we could have obtained what is that lambda y dot 1 plus y. For higher order functions, it is easier to pass partially applied functions as parameters. So, a higher order function is a function that takes one or more function as arguments or returns a function as a result. For example, we want to first increment a value y, then we want to square it. So, we write it in this way. So, it is a higher order function because these two are functions, whereas y is a variable. Now, it provides code reuse and clarity, avoids needing multiple versions of similar functions. So, in Haskell, we can write this add function in this way. So, at Haskell, we write the name of the function and this is the signature. That means what it says, it takes integer as input and it returns a function from integer to integer, or you can read it as there are two input that are of type integer and returns an integer. So, add xy, this is the body of add, it says add xy is be x plus y. Now, we want to say what is add 1. Now, is it correct to say add 1? Now, that means we are doing partial application of function. If I do add 1, it will be y has not, value of y we have not yet passed. So, it is 1 plus 1, which is the same as add 1 lambda y dot y plus 1. So, this is legal and this is permitted in functional languages. This is called partial application of function. Now, if you see uncurried, so we are used to working with uncurried. So, if uncurried xy is x plus y, here the idea is both the arguments are to be supplied together. So, in imperative programming languages, this is the idea. So, when the actual parameters are passed, we are putting them together rather than a partial. So, let us summarize the ideas that we have studied. So, we have studied the motivation behind the development of the lambda calculus. We have studied the equivalence of Church model and Turing model of computation, the notation in lambda calculus, the lambda notation, partial application of functions and currying, and the influence of lambda calculus on functional programming languages. Here are some recommended books and articles. So, all throughout this course, we are going to follow these books and also provide pointers to other articles during the course of time. So, the first book is by Ravi Sethi. That is a very nice book, and for studying programming language, you can take a look at this book. Now, when you are going to study simple type theory, we are going to follow the Roger Hindley's book. Also, the elementary ideas of computation or lambda calculus, we are going to follow from Roger Hindley's book. John Mitchell's book, Foundations of Programming Languages, is another very nice book. So, we will also follow, refer to this book for some additional concepts. Then we also have an article by Barendrecht, which is appeared in Handbook of Theoretical Computer Science, Volume B, Functional Programming and Lambda Calculus. Thank you for your kind attention.